This video is meant for Mrs. Rose's AB Calculus class, and it is our introduction to related rates. Related rates is basically implicit differentiation in some kind of real-world context with respect to time. The derivatives are all with respect to time. Our objective is to see that y'all will understand how rates of change can be related, and you'll be able to use implicit differentiation to find the rate of change of two or more variables changing with respect to time. The basic idea was our snowball problem. So if the snowball is melting and our volume is decreasing, well, the size of the radius of our sphere is also decreasing. So as volume goes down, the radius goes down too. Those rates of change are related. Okay. We did this matching activity in class where we have the equations for different types of geometric functions and their derivatives. So if you want to pause the video when I'm done erasing and write these down as a reference, that could be helpful. Otherwise, you can always look in your textbook as a reference for the volume of a cylinder, etc. And you can always take the derivative using implicit differentiation. So now we're going to look at some word problems, and you should have a follow-along sheet that matches these problems. Alright, we've got a rocket. It is rising vertically. So I'm going to draw a picture of a rocket rising vertically. And it is tracked by a radar station that is on the ground 5 miles from the launch pad. So we know that this distance is 5 miles. How fast is the rocket rising when it is 4 miles high and its distance from the radar station is increasing at a rate of 2,000 miles per hour? So we want to know, determine the rate of change you are trying to find. We want to know basically how fast this is rising. So if we use Pythagorean Theorem, we can use dB dt. You can really label it whatever you want to, but we can call this B, and we want to know what dB dt is. So we have A equals 5, C equals, we don't know yet. And then we can fill in some other rates that we were given. So we know that the rocket is increasing its distance from the radar station at a rate of 2,000 miles per hour. So we know that dc dt equals 2,000 miles per hour. We also know dA dt. The distance between the launch pad and the radar station is constant. It's not changing. So the rate of change of something that's not changing is 0. Alright, so I think we have all of our things we know and definitely don't know, dB dt. And so we want to be able to write an equation that relates two or more of our variables that are changing with respect to time. So we've already mentioned it, but we're going to be using the Pythagorean Theorem. So we've got a squared plus b squared equals c squared. Since a is not changing, we can go ahead and plug in 5. And then the fourth step is to take the derivative with respect to time. So the derivative of 5 squared, or 25, is just going to be 0. And then we've got the derivative of b squared is 2b dB dt. Again, the derivative is with respect to time. And the derivative of c squared is 2c dc dt. Okay. So step 5, we want to solve for the rate of change by plugging in the known information given. So we've got our derivative 0 plus 2, b is 4. Oh, didn't write that above, but we definitely have b equal to 4 because the rocket is 4 miles high. We don't know dB dt. And we know that this needs to equal 2c dc dt. And we plug in dc dt. We don't know what c is. But that's easy enough to figure out. We have the Pythagorean theorem, so if we need to find c, we just plug in 4 and 5 respectively, and we calculate what c is. And then we're going to plug it into our derivative equation. So we have 8 dB dt equals 2 times the square root of 41 times 2000, and then we're going to divide both sides by 8. This is an acceptable answer. You need units, but if you're trying to make sense of the problem, you can change it to decimals. You need to make sure you have at least 3 decimals, and then you need to have your units miles per hour. So that's 3,201.5612 miles per hour. Okay. To summarize the steps we just did, those are here. Those were on the previous page before I erased them, and now I'm moving on to the next problem. Okay, point is moving along the curve y equals 2x cubed minus 5x. So the x-coordinate is increasing at a rate of 3 units per minute. At what rate is the y-coordinate changing when x is 4? Alright, so we know a couple things. They said the x-coordinate is increasing at a rate of 3 units per second. So that's going to be the change of x with respect to time, and that is positive 3. It's increasing. What is the rate of change of the y-coordinate when x is 4? So we know x is 4. And the other thing we know is the equation they gave us, y equals 2x cubed minus 5x. What they want to know is the rate the y-coordinate is changing, so we want to know dy dt. So all we're going to do is take the derivative of y equals 2x cubed minus 5x with respect to time. So we've got dy dt equals 6x squared dx dt minus 5 dx dt. And then we just plug in the information that we know. So we don't know dy dt, but we know x, we know dx dt, and then it's just a matter of evaluating it. And because we were given dx dt in units per second, dy dt is also going to be in units per second. For our third example, it's very similar to the snowball problem we've been working on for months, but it's asking a little bit of a different question. We've got a spherical snowball that is melting so that its volume is decreasing at a rate of 5 cubic inches per minute. So we know that dV dt equals, negative 5 inches cubed per minute, and we know it's negative because the volume is decreasing. And then we continue. At the instant when the radius of the snowball is 4 inches, what is the rate of change of the surface area of the snowball? So r is still 4, but we want to know what the rate of change of the surface area is. So we can go to our surface area equation that equals 4 pi r squared, and then we can take the derivative, which is 8 pi r dr dt. The problem is we weren't given dr dt, and we want to know dsa over dt. So we could go ahead and plug in 4, but that's not going to really do anything since we don't know dr dt. We do know dv dt though. So if we use the volume equation of a sphere, we can take the derivative and plug in negative 5 for dv dt, and then plug in 4 for r and solve for dr dt. So we have negative 5 equals 64 pi dr dt, and so negative 5 over 64 pi equals dr dt, and now we can plug that into our surface area derivative. dsa equals 8 times pi times r times dr dt. So we have 32 pi times negative 5 over 64 pi, which is negative 5 over 2, and it's inches square per minute. For our last example, please refer to the next video, and if you have any questions, please see me during Chem Morning.